Okay, just before we start today, the book we were working out of is this one, and all the questions and answers are going to be available in a link, hopefully just here. Hi, welcome to Garden Mechanics with me, Mr. Whitworth. Now, at the start of every episode, we're going to have a challenge for you, an idea to think about, and we'll give the answer at the end of the episode. So today, we have a bike. And if you zoom in, or come in here, I'll show you what we're doing. So I've got a rope attached to the pedal, and I'm going to put the crank at its lowest position here. Now, if you zoom back out, thank you very much. All Caitlin's going to do is stabilise the bike. She's not going to hold it or move it anyway, she's going to stop it tipping over. Now, if I was to pull this rope in this direction, which way is the bike going to go? Find out at the end of the episode. Mechanics. This week on Garden Mechanics, we're going to be looking at Newton's laws, resolving forces, and finding accelerations. I said drop it like I'm like. While Sir Isaac Newton was at Cambridge University, he was actually sent home during his studies because of an outbreak of the bubonic plague. During his time at home, he came up with his 3 laws for motion. We're going to explore Newton's 3 laws of motion and then see how we can apply them to questions. So Newton's first law of motion is that an object will either stay at rest or move with a constant velocity unless an external force acts on it. So a big misconception of Newton's first law is that if the forces are equal, the object doesn't move. Now this isn't always true. An object can be moving with a constant speed if the forces are in equilibrium. Here's a fairly easy example of Newton's first law. We have a deer standing on a table. The deer isn't moving, so the forces are balanced. So in this example, we have a strongman event called the Pillars of Hercules. Now, quite clearly in this case, Felix, our strongman, is having to exert a huge amount of force to hold these pillars up. But crucially, there is no resultant force, nothing is moving. So there is force, but there is no movement. We call this static equilibrium, and we'll be looking at more static problems later in the course. Here's an example of forces in equilibrium while there is constant velocity. These paratroopers are jumping out of an aeroplane, and as they move towards the ground, they are travelling at a constant speed. This is because the force, which is their weight, is being counteracted by an air resistive force, and they are travelling at a terminal velocity. So they're moving, but the forces are in equilibrium. And this is quite helpful because it means that they land safely on the ground. This is one that you've probably experienced yourself. If you are travelling in a car and the car is doing a constant velocity, you will not feel any force forwards or backwards. The driving force and the resistive forces are in equilibrium. And we can actually see this with a Newton's cradle in a car travelling at a constant speed. There is no resultant force. Okay, here's something you can try at home. It's called an inertia stack, and it shows Newton's first law. 2 forces equal and opposite in direction create a net force of 0. So Newton's second law. If I have an object with a mass and I apply a force to it, its velocity will change. It will accelerate or decelerate. This can be expressed using the formula F equals ma, and rearranged, the acceleration is the force applied divided by the mass of the object. F equals ma will be the basis of all the force work we do. You'll get used to it very quickly. One thing to talk briefly about is that if we have force equals mass times acceleration, then we can actually define weight using the same formula. So weight is a force, and weight is mass times gravity. So in this case, the acceleration is g, or gravity, so therefore weight is a force. Don't get confused, mass is a physical property, but weight is a force. So here's a really nice example of F equals ma. We have a rocket which has a huge weight, and it has to produce a huge amount of thrust or force in order to accelerate it away from Earth.
Thrust! I've had birds like ducks and geese when they take off, what do they have? Thrust!
Well, of course we need thrust. Thrust and flying are like this.
Going back to our car example from earlier, if I am to accelerate, to have more driving force forward than resistive force backwards, we have a resultant force, and you can see this on the Newton's cradle. In a similar way, if we slam on the brakes, we get a bigger braking force than a driving force, and therefore we have a resultant force in the other direction. Okay, so here's a really good example of Newton's second law, F equals ma. You will have seen this in GCSE. It's a required practical for GCSE, so you would have seen it before. And all we're going to do is we're going to explore how the force here is going to make this trolley accelerate. One thing to notice is that the whole system weighs 1.5 kilograms, so that's the trolley, these masses and the hanger, and it's important that we keep that constant so that we can get some good results for the acceleration. The data logger here is going to use a light gate to record the acceleration, and all I'm going to do is increase the applied force by moving a mass from the trolley to the hanger and then see what acceleration that gives us. So there's our first one. If I plot that point, I'll go through and do all of them nice and quickly. As we can see, as I increase the force or increase the mass here, I'm increasing the force and therefore increasing the acceleration. And we should notice something about the graph that's being drawn. Wow, what a lovely graph. Amazing. So what we should notice is that the force applied and the acceleration have a direct proportion. So as I increase the force, the acceleration also increases. The other thing to notice is if we think about our formula, the acceleration is going to be the force divided by the mass. Now the force we're controlling here, if we divide that by the mass, which is 1.5, we should get our acceleration. So if we have a look, we have 3 here. Here's a good example. So force is 3 newtons. We divide that by the mass, which is 1.5, and we get our acceleration, which is 2. Now, this is a really nice way of showing that we have direct proportion between the two, and it shows the relationship of F equals ma. The gradient of this graph is a little bit difficult to see because we're kind of the wrong way around, but if I did the force divided by the acceleration, the gradient will be 1.5 all the way along. Third and final law. For every action, there is an equal and opposite reaction. This is probably the one you've heard before, and it's quite an obvious one really, but it's probably quite interesting to see what happens when this law doesn't exist. So, have a look at this clip. So that looked weird because there was no equal and opposite reaction by the ball on the left-hand side. The Newton's cradle is a really good way of showing Newton's third law. For every action, there's an equal and opposite reaction. In this last example, I'm pushing off with my foot, pushing forward my other foot, and they are happening in equal and opposite directions. Time for some work. I want you to have a go at this worksheet. The link is below. You'll need to use all 3 of Newton's laws, as well as your knowledge on SUVAT equations. Good luck, the answers are attached.
Mechanics.
Okay, so we're going to look at resolving forces, which means combining forces, subtracting and adding them in order to find a single force component which causes an object to accelerate. What we're watching here is the SpaceX rocket coming back down to land, and it uses lots of small boosters as well as its main propulsive rocket at the bottom in order to land vertically so it doesn't damage itself and it can get used again. We're going to look at some simple examples of resolving forces before we dive into some more difficult questions. Okay, for this first question, we have a particle of 2 kilograms, a force of 10 newtons and a force of 2 newtons. This is quite a simple example to start with. If I redraw my particle, I have 2 kilograms here. Now the overall net force is going to be 10 minus 2, so it's 8 newtons. If I start with F equals ma, I can work out what the acceleration is. So the resultant force is 8. That equals the mass, which is 2, times the acceleration. So the acceleration is 4 meters per second to the minus 2. Okay, in question 2, if we have a look here, there's some information here at the top which helps us. This is a static problem. There's no acceleration in any direction, which means there's no resultant force. Therefore, if I resolve horizontally, then I have 15 minus y equals 0, because there's no resultant force that way. If I solve this, that gives me y equals 15 newtons. If I resolve vertically, this notation is really useful when you're resolving forces, so get used to writing that. So if we look vertically, we have 12 minus x, and that must equal 0, as there's no vertical acceleration, therefore x equals 12 newtons. Okay, so in this question, we have two forces, and to resolve these forces, we need to think about where this object's going to go. It's going to come down here somewhere. Okay, we're going to need to use Pythagoras and trig to work out what the resultant force is and in what direction it's acting. So let's work out what the resultant force is first. So if I draw my 8 newtons this way and I add my 5 newtons in this direction, my resultant force is going to come along here. Now what we've made here is a right angled triangle. This length here is 8, this length is 5, so we need to use Pythagoras to find what this length is. So we do the square root, 8 squared plus 5 squared, and that gives me an answer of about 9.4 newtons. Okay, so that's what the resultant force is. The question is, in what direction is it acting? So we need to find this out as a bearing. So if I draw my triangle again, and to work out this missing angle, I need to think about trig. I've got the opposite side and the adjacent side, so x is going to need to use tan. So x is going to equal tan to the minus 1 of opposite over adjacent. This gives me a nice answer of 32.00 degrees. So to find the bearing, if we go from north, we're going to go around 90 degrees and then our 32. So this gives me a bearing of 122. Okay, so my final answer is that resultant force is 9.43 newtons on a bearing of 122. So there's a lot more work to it when you have an angled force. Okay, the last example from me before you get on with your own work is this one. We have a static problem, the particle's at rest. We have an 8 Newton force at 30 degrees, and we have this unknown force x and an unknown force y. Now the whole thing is going to balance. So a bit like the last question, we're going to look at this component first, but we're going to work backwards. So if I draw my 8 Newton force here, and I draw a force horizontal and a force that's vertical, I can work out what these component forces are. So this one here, this is the opposite side, this is the hypotenuse, so this must be, using the sine ratio, this must be 8 sine 30. This one here, the adjacent side, must be 8 cos 30. So I've got my vertical component and my horizontal component. I can draw out my diagram again. In this direction, I have 8 cos 30. In this direction, I have 8 sine 30. In this direction, I have the unknown force x, and in this direction have the unknown force y. Now, because we're in equilibrium, this force must equal this force, and this force must equal this force. So it's not too difficult. X must equal 8 cos 30, which as a decimal is 6.93 to 2 decimal places. And similarly for y must equal 8 sine 30, which is 4 newtons. Okay, so because it's static, we work out these components here, and then we balance them with these two forces here. Okay, we need to practice resolving forces. It's task 2 on your worksheet. Have fun. Okay, so using this 2 kilogram block, we're going to think about vertical motion. So we're going to see what happens when we have a force going upwards. We're going to think about when it accelerates downwards and what that means. And finally, we're going to think about constant speed and what that means in this vertical motion situation. We start with our block at the bottom. And the force that I apply is going to be greater than the weight going downwards. We find that T is greater than 2g, so the resultant force is T minus 2g. In the second situation, the weight downwards is going to be more than the tension upwards, and you'll see what happens. So by resolving vertically, we find that the 2g is greater than the t, so the resultant force is 2g minus t. Okay, in the final situation, the weight and the force are in equilibrium, so we get a constant speed. In the final case, we find that resolving vertically gives us a resultant force of 0, so T must equal mg. Let's use these concepts and apply them to some questions. It's task 3, have a go. Okay, so here's a challenge. We're going to accelerate this block from here to here, which is 60 centimeters. Once it hits here, I'm going to remove the force that's accelerating it. What I want you to do is find out how high it goes above this point. Okay, we're going to time it, which will allow you to work out the acceleration, and the rest of it's up to you. Ready? 3, 2, 1. Have a go at this question in your own time. I'll provide a worked solution as a separate video. Okay, so the next thing to look at is horizontal planes and how particles move on a horizontal plane when we apply forces to them. So here's my particle. It weighs 338 grams. And our plane here, we're going to model as being completely smooth. Obviously, that's not realistic, but it's a good modelling assumption to make at the moment. The first thing to think about with any horizontal plane question is that our particle is going to exert a force from its weight this way into the surface. And because of Newton's third law, the surface is going to do this. It's going to push it back with the same amount of force. So you always need to write on your weight and your reaction force straight away. So a simple situation to start with. If I have a force going this way, which is pulling my particle along, and I have a resistive force going this way, if they are equal, thinking about Newton's first law, I have either a static situation like this, or I have a constant speed. Okay, if they're both equal and opposite, I either have a constant speed or I have static. Now, if this force is greater than this force, this happens. The overall resultant force is this way.
Okay, in the other direction, that would happen. Okay, and we can work that out fairly simply. All we do is we do this force, which is bigger, we take away the smaller force, we divide by the mass, which is here, and that works out our acceleration. So I'm going to use an accelerometer on my phone. What we should see is a flat line because nothing's moving. If I accelerate this, I provide a force in this direction, I should see a spike on my accelerometer. So if I pause that, let me have a look. We see that it accelerated at about 0.8 meters per second squared. So we can actually quantify the acceleration there, and therefore we could work out the force. So if I weigh this whole system, it comes to 540 grams.
If I multiply this mass by the acceleration we measured, I get a force of 0.432 newtons.
So a more complicated situation would be that if this force doesn't act horizontally to the surface, it actually acts at an angle. So if the force pulls my particle along like this, we need to think about all the forces that are going on. I have a component which is going upwards, and I have a component which is going horizontally. This horizontal component will dictate the motion of this particle along the surface. This vertical component actually pulls up on the particle, which makes it lighter. It reduces the contact force from the surface. So if you can imagine I had this at a really high angle, and I pull hard enough, it's going to lift up. But if I pull at less of an angle, we can see that force becomes more this component and less this component. We're going to do an example. If I measure this angle, and I'll try and make this as accurate as possible, let's say it's 30 degrees, about there. If I pull this with a force, let's say a force of 5 newtons, can we work out the reaction force, and can we work out the acceleration in this direction? Okay, so for this question we have a force acting at 30 degrees above the horizontal. There's a force of 5 newtons. And in this question we want to find out the acceleration this way and also the normal reaction force. So the first thing we're going to do is I'm going to label up the other forces on this diagram we need. So the first thing to do is to split this force up into its component parts. So we have the vertical component, we have the horizontal component, we also have the weight of this particle acting downwards and its reaction force acting upwards. So we have the reaction force, we have the weight, which is 0.338 g. We have the vertical component, which is 5 sine 30. Think about your trig ratios. You have this horizontal component, which is 5 cos 30. And now we've got that all labelled up, we can have a go at these questions. So, first question to have a go at, let's work out that acceleration. First thing to do, resolve the forces horizontally. So we have this 5 cos 30 and no other horizontal forces. So, the resultant force is 5 cos 30. If we put this into our F equals ma, we get 5 cos 30 equals our mass, which is 0.338, times by acceleration. If we divide our resultant force by 0.338, we get our acceleration, which is 12.8 meters per second to the minus 2. So for part B of this question, we need to think about what's actually going on. So this force here, this 5 sine 30, is reducing the weight on this surface. So we should expect an R value, a reaction force, which is less than the original weight. Okay, so keeping that in mind, let's have a think about resolving the forces. So resolving vertically, the forces acting upwards are R plus 5 sine 30, and they must equal the forces down. It's just one force, 0.338.
4.38G. Okay, have a little think about this equation. These two forces are acting upwards, and this force is acting downwards. Now they're equal because there's no acceleration upwards. So if I solve this, I have R equals 0.338G, take away 5 sine 30. Now this should make sense because this means we're going to get a value which is less than 0.338. And if we work this out, we get an R value of 0.81 newtons.
The last force to talk about is one that's going down like this. So if I was to push my particle down at an angle, we need to think about what's going on. So again, I have these two components. I have a component going this way, which is causing it to move along the surface. But I also have a component going down, which is making this heavier. This force plus the weight means I have a bigger reaction force. So again, let's have a look at a question. Let's say that I'm pushing down with 5 newtons of force, and this angle here is 45 degrees. Let's work out what this acceleration is. Let's work out what this reaction force is from the surface.
First thing to do is to label up all the forces that you've got. So my vertical force down, my horizontal force component, my weight, and my reaction force. Okay, so I'll label these up now. This one is 5 sine 45. This one here is 5 cos 45. This is my weight downwards, my 0.338G. And this is my reaction force upwards. Okay, so for part A, we resolve horizontally to find the acceleration along the plane. We have one horizontal force, which is 5 cos 45. If I use F equals ma, I have my resultant force, which is 5 cos 45, and that equals 0.338A. Therefore, my acceleration is 10.46 meters per second to the -2. Okay, part B. In this case, we need to resolve vertically. So if we think about the forces going upwards, we only have our R going upwards. So we can write R as our upwards force must equal the downwards forces. So the downwards forces are the weight of the particle, 0.338G, plus that vertical component that we've worked out, 5 sine 45. So notice in this case, we are adding to the weight of the particle because we are pushing down with this force. So our resultant force, our reaction force from the surface must be bigger than the weight. Okay, so our R, which is our reaction force, is going to equal 6.85 newtons.
Okay, so with a horizontal particle, I can have forces going at all angles, I can combine them, and I can work out what the overall acceleration is and what the overall normal contact force is. Have a go at some questions and see how you get on.
Also have a go at task 5, which is some wordy questions using Newton's laws. There are full solutions provided in a separate video. So, the moment we've all been waiting for. Which way is this bike going to go? Let's find out. So, if that's surprising, consider the whole system. Ignore all the pedal, all the gears. There's one force acting on this whole system and it's going this way. So the whole system has got to go this way. Okay, that's it for week 1 of Garden Mechanics. We looked at Newton's laws, we looked at resolving forces, vertical motion, motion on a plane, and you've had a go at some questions. Remember, all the work is available in the workbook, and there's 2 extra videos of work solutions.
See you next week.
Mechanics.
Mechanics.
Mechanics.